Hi everyone, welcome back. In this video, I will show you how to run a two-way ANOVA in R. Remember that a two-way ANOVA is an ANOVA analysis where you are trying to see if two factors influence an outcome variable, all right? It's called two-way ANOVA because we are studying two factors. Also, remember that factors are categorical variables whose values don't represent numerical quantities. They represent labels, okay? That's what factors means. Now, in a two-way ANOVA, when I said we are studying the influence of two factors on an outcome variable, what do I mean by influence? Well, by influence, I mean that we want to find out if the average value of the outcome variable changes for the categories of each of the two factors. That's what we're trying to find out. We're going to work on an example right now, and after you explore that example, you will better understand what a two-way ANOVA is, okay? All right, so let's jump into R. Notice that I'm actually using RStudio, and using RStudio, I created this notebook, this .rmd file, and I did all my analysis in this notebook. I'm going to share this notebook with you via the description of the video. And you will be able to check out all the code that I included in this notebook. So in this video, I'm not going to focus that much on the code, but I'm going to focus mostly on the explanations, okay? All right, what problem are we trying to solve here? So here we have data from a farm scale trial of animal diets, and we are studying two factors, the diet and the supplement. We are studying three diets, barley, oats, and wheat, and we are studying four supplements, Agrimore, Control, Super Gain, and Super Sub. The outcome variable of interest is the weight gain after 6 weeks. And what we want to find out is the possible effects of diet and supplement on the animal's weight gain. That's the outcome, animal's weight gain. Okay. All right. The data for this problem, I have it in this CSV file. I have this CSV file, growth.csv, stored locally. So I'm going to read that CSV file as a data frame using the read.csv function. And for that, I'm going to set the option string as factors as true, because if you want to run ANOVA in R, you need to make sure that all your string columns are transformed into factor data type. So they should have a factor data type, okay? All right, so let's run that code cell to read the CSV file as a data frame. Now let's take a look at, let's take a look at the data frame. Okay, let's take a look at that data frame using the structure function. And sure enough, we see that our data frame has 48 observations. So we have data for 48 animals and 3 variables. So the first one is supplement, factor data type, okay? Diet, factor data type, and gain, which is numeric, which is our outcome variable, okay? All right, so before jumping to running the ANOVA test, I advise you to always do this when you are doing a two-way ANOVA. Estimate the mean of the outcome variable for both each factor level and for each combination of factor levels, okay? That means that I am advising you in this case to obtain the sample mean weight gain for all supplements, the sample mean weight gain for all the diets, and the sample mean weight gain for the combination of diets and the combinations of diet and supplement, okay? All right, here using the tapply function, I'm gonna get the mean weight gain for each supplement, okay? All right, those are our first supplements. So this is the mean weight gain for super gain, mean weight gain for control, and so on and so forth. Notice that they are different, right? The sample means are different, right, for each supplement, right? But guys, remember that these differences are being observed in a sample. We don't even know if these differences are real, meaning like, do these differences hold at the population level as well? So do we expect to observe these differences like between super gain and control and between control and super sub and so on and so forth? Do we expect to see these differences in future samples that we might take in the future? You know what I mean? Like if we keep taking samples, not only this one, but other samples, are we gonna keep observing these differences between super gain and control or not? Maybe the difference will disappear, okay? So what we need to find out is if the difference are statistically significant or not. And to find that out, we need to test two hypotheses. We need to test the new hypothesis that the the population mean weight gain for all the supplements is the same versus H1 that there is a difference in the population mean weight gain for at least two of the supplements, okay? And we're gonna be able to test these two hypotheses from the ANOVA results, okay? And then we repeat the same thing. So we estimate the sample mean weight gain for the diet, okay? And one more time, they are different. So the sample means are different for the diets, but are they statistically different? To find that out, um, we need to run or we need to test these two hypotheses, okay? We need to check HO, the population mean weight gain is the same for all three diets versus that at least two diets have a different mean weight gain, okay? And finally, a third effect, let's say like that, a third effect that we can check for is the interaction effect between diet and supplement. What do I mean by that? So let's take a look at the sample mean weight gain for each combination of supplement and diet, okay? That's the sample mean weight gain for each combination. And let's take a look at, for example, if we are using Agrimor, okay, if we're using Agrimor, when we change diet from barley to oats, what happens? Well, we see a decrease of around 3 units in weight gain, okay? But what happens if you're using Super Sub as a supplement? What happens if you're using Super Sub and we change diets from barley to oats? Well, now we see a decrease in around 4 units, okay? Before it was 3 when we used Agrimor, but when we use Super Sub, it's 4 units, okay? All right, so there is a difference there. What happens, for example, if we use Agrimor and then we change diet from oats to wheat? Well, we see a decrease in around 3 units. But if we use Super Sub and we change from oats to wheat, we see a decrease in only 2 units. So what's going on there? Are those differences significant? Well, if the change in weight gain as we change the diet depends on the supplement, okay, in a significant manner, then we can claim that there is an interaction, okay? So for the interaction, the hypotheses that we're testing are no interaction between supplement and diet, and that means that the effect of changing diet on weight gain does not depend on supplement, versus that there is an interaction, and what that means is that the effect of changing diets on weight gain depends on the type of supplement, okay? So we're gonna test for 3 hypotheses, for 3 effects, I'm sorry. The effect of diet, the effect of supplement, and the effect of the interaction, okay? All right, to test for those 3 effects, we can run this ANOVA analysis using this code. And once you run that ANOVA analysis, all you have to do is you need to look at the p-value. So to know if the effects are significant or not, look at the p-values. So for example, let's evaluate the supplement effect, okay? For the supplement effect, we look at supplement, the supplement row, and we look at the p-value for supplement. The p-value for supplement in scientific notation is 2.95 times 10 to the negative 7. That's a tiny, really, really tiny p-value. So obviously that p-value is less than alpha, okay? That p-value is less than alpha, and what that means is that we can reject HO and support H1. So if we support H1, we can conclude that there is a difference in the population mean weight gain for at least 2 of the supplements, okay? So the difference in supplements is significant, okay? And then how about diet? Well, the p-value for diet also very small, okay? So p-value less than alpha, okay, which in this case, that's what happens, p-value less than alpha, we reject HO and support HA, okay, or H1. And remember that this is scientific notation, so this is a really, really tiny p-value, okay? All right, so for diet, we can also claim that the population mean weight gain is different for at least 2 diets. So both diets and supplements have a significant effect on weight gain, but the interaction is not significant. The interaction is not significant. This is the row for the interaction, guys. Okay, and you can see that the p-value is way, way above alpha. P-value greater than alpha, we cannot reject HO. And if you do not reject HO for the interaction, okay, what are you saying? Well, you are kind of sticking with this. You're stuck with this conclusion, no interaction effect. So the effect of changing diets on weight gain does not depend on the type of supplement. So the effects that I was mentioning earlier when we looked at the table, okay, these possible effects that I was describing here, those effects were not significant, okay, because the interaction is not significant, okay. Perfect. So we know diet has a significant effect, supplement has a significant effect. Interaction, no significant effect. What do we do in that case? Well, in this case, we should do a post-hoc test individually for each factor. So one for diet, one for supplement, okay? And to do the post-hoc test, I'm going to use the Bonferroni test, okay? So you can use other post-hoc tests like Tukey, but I'm going to use Bonferroni. If you want to understand the Bonferroni test a little bit better, you can watch one of my videos. I have a video in my channel titled Bonferroni test, and I explain like how to do the Bonferroni test step by step. Okay, so go ahead and watch that video to understand the Bonferroni test a little bit better. All right, so Bonferroni test for diet, Bonferroni test for supplement, both. Let's start with supplement, okay? This is the Bonferroni test for supplement using this function. Again, check out my video, my previous video, so yeah, so that you understand what that code does. Okay, that's the output from the Bonferroni test, and what we need to look at here is the p-values below alpha, p-values less than alpha. But there is only one p-value less than alpha in that matrix. That p-value is the only one that is less than alpha. So that's why I said here, the only significant difference with respect to the mean weight gain is between super gain and Agrimore, okay? That p-value corresponds to Agrimore and super gain, okay? So that's the only significant difference, all right? Now, if you remember, let me show you the means again. Those are the means for the supplements. So we just found out that the only difference, significant difference, is between super gain and Agrimore, okay? The other differences between control and super sub, control and Agrimore, so on and so forth, they are not significant. So since we're looking for a high weight gain, that's the most desirable option, Agrimore is better than super gain, okay? So they are significantly different, super gain and Agrimore, but we're looking for the higher the better, so we can claim that Agrimore is a better supplement than super gain. We repeat the same post-hoc test, Bonferroni for diet, and in this case, all p-values are less than alpha. Again, this is scientific notation, so all of those p-values are less than alpha, right? So we conclude that all diets lead to a statistically different average weight gain. And when we look at the means, again, the sample means, again, this is what we get, okay? So the highest mean for barley, then second highest for oats, and then the lowest for wheat. Since we're looking for the highest possible mean weight gain, so we can claim that the best diet is barley, the second best diet is oats, and the worst diet is wheat. Just because they are all significant, okay? So since they are all significant, we can kind of establish that hierarchy. We could not establish that hierarchy here. So we cannot claim that Agrimore is better than Super Sub. No, because the difference between them is not significant according to Bonferroni, okay? We cannot claim that Super Sub is better than Control. No, because the difference between Control and Super Sub is not significant, okay? Based on the p-values that we saw here. The only thing that we can say for the supplement is that Agrimore is better than Super Gain because the difference between them is significant indeed, okay? But for the diets, all the differences are significant. So we can claim that barley better than oats, oats better than wheat, okay? All right, guys, so to finish, what is our final conclusion here in terms of what is the best diet and supplement to use? Well, obviously the best diet is barley, we know that. And in terms of the supplements, the best you can say is that don't recommend super gain. Don't recommend super gain because we saw that super gain was worse than Agrimore. But in terms of the best supplement, that's a little bit more tricky to decide. But at least you can say that in principle, either control super sub and Agrimore should work. Okay, but super gain, no. Okay, so the final conclusion is that the overall suggestion is feed the animals with barley and either Agrimore, super sub, or control, but do not use super gain. Okay. All right, guys, that's all for this video. In this video, we saw how to do a two-way ANOVA in R. And I hope you enjoy it. And I will see you in another video. Bye, guys.